Hi everyone, this is the video for class 35 of PH 125, and this is going to be our last video lecture for the semester. So we're going to be wrapping things up today by talking about entropy and the second law of thermodynamics, and then we're going to finish off by talking about engines and refrigerators. Alright, let's start our discussion of the second law of thermodynamics today by talking about reversible and irreversible processes. So we'll start with a reversible process, which is basically what it sounds like. So imagine you have some system and you imagine some process that transforms the system from one state to another. When you have a reversible process, if you were to reverse that process, then you would end up getting your system and the surroundings back in the original state. Okay, and so what that means is you could think about taking a video of that process as the state is transformed in the forward direction and then playing it backwards, and it would look the same. So it wouldn't look like anything strange was happening when you played the video in reverse. All right, let's think about some examples here. So examples include microscopic collisions, so collisions of particles. Compressing and stretching a spring, you can see, is also going to be a reversible process. So if you were to play this top video in reverse, it would look exactly the same. There would be nothing weird looking about it. And it turns out that isothermal expansion and compression of a gas is also a reversible process. Okay, now let's talk about irreversible processes. So for an irreversible process, what happens is if you imagine having a system and the surroundings and the system is initially in some state, then you do some irreversible process that changes the state of the system to some new state. Then if you were to imagine reversing the process that was just done on the system would not go back to its original state, and the surroundings wouldn't either. So this is the characteristic property of an irreversible process. Another way to think about an irreversible process is if you were to take a video of that irreversible process happening that transforms the system from one state to another, it would look very unphysical if you were to then play that video in reverse. So that's unlike the reversible processes where you would play the video in reverse and it just would look natural to you. If you were to play an irreversible process in reverse, it would look like something was wrong. You would get some red flags. Okay, so let's talk about some examples of what I mean there. So classic example of an irreversible process is the spontaneous flow of heat from a hotter object to a colder object. So for example, if you were to imagine placing an ice cube into a glass of water. Okay, then you were to imagine thinking about that ice cube in the glass of water, taking a video of it melting. And then you play that video in reverse and you start off with a glass of water and then it would form an ice cube. Okay, and so that would be something that would be unphysical looking to you, played in reverse, right? And so that would tell you that that's an example of an irreversible process. Another example of an irreversible process, you can imagine having a bouncing ball. So imagine you have a basketball and you give it a bounce and then you stop touching it, so you stop making it bounce. Eventually that ball would come to rest on the ground. Okay, and so I have this video on the right-hand corner of the slide here where you can see you have a ball, it bounces, and then eventually it comes to rest. If you were to play that video in reverse, you would have a ball sitting on the floor that spontaneously starts bouncing. Okay, and this is something else that we know just wouldn't happen physically, and so that would be another example of an irreversible process. Okay, and so now we want to know, why are these processes irreversible? It's tempting to think that it's because energy isn't conserved, maybe there's some energy loss, but actually universally energy has to be conserved. So total energy is still going to be conserved in both the case of the heat flow and the bouncing ball here. It's just going to be changing forms. Okay, and so there must be something else that prevents the ball from spontaneously bouncing and something else that prevents the heat from flowing from the colder object to the hotter object. So we want to know, what is that thing? Well, it turns out that the reversibility or irreversibility of a particular process is related to a property called entropy. So entropy, it's given the symbol S, and oftentimes it's defined as a measure of disorder. Alternatively, it can be defined as a measure of the ways of arranging the elements of a system. Okay, so we're going to see in a little bit that entropy has units of joules per Kelvin, and so that tells me that the entropy is also somehow going to be related to energy per unit temperature. It turns out that it's going to be the energy per unit temperature that's unavailable to do work. Okay, so that's another way to think about the entropy. Okay, and then entropy is what we refer to as a state variable. So remember, other state variables that we've talked about are things like pressure, volume, temperature, and internal energy. So state variables in general only depend on the state of the system. So it doesn't matter how a system got into a particular state. All that matters is what state the system is in determining these state variables. Okay, and so entropy is one of these state variables. And then this tells us something special when we think about a cyclic process. Remember, when you have a cyclic process, the system is going to start and end in the same state. And so then when you think about the change in entropy for a cyclic process, the total change in entropy has to be 0 since the system starts and ends in the same state. All right. Next up, let's talk about some examples of processes that increase entropy, just to kind of get a feel for this definition of entropy. So remember, entropy is a measure of disorder. So something that increases disorder, for example, would be melting ice. So when you think about melting ice, ice forms really rigid crystals. So they're very, very organized crystals. And then when you melt the ice turns into water and the particles bounce around all over the place. They're very disorganized. And so when you think about melting ice, you're increasing disorder and you're increasing entropy. So that's where that thought of entropy as a measure of disorder is really coming from. All right, then specifically for a quasi-static process, which is a process that's usually slow and reversible, it turns out that the change in entropy of a system, delta S, during that particular process is exactly equal to Q, which is the amount of heat that flows into the system if Q is positive or out of the system if Q is negative, divided by T, the temperature of the system, where T is the temperature and is measured in Kelvin. All right, so let's do a little bit of practice with this idea of the change in entropy of a system due to heat flow into or out of a system. So here we have a hot 98 degrees Celsius slab of metal placed in a cool 5 degrees Celsius bucket of water, and we're going to assume that the system is isolated, where the total system is going to be the slab plus the bucket of water. Okay, and we want to know, first of all, what happens to the entropy of the metal? Okay, so to answer this question, I would be thinking about the equation delta S is equal to Q divided by T, where delta S is the change in entropy of a system, or in other words, you could rewrite that as S final minus S initial. Okay, and so then when I think about if the entropy is increasing, decreasing, or staying the same, what that really means is delta S going to be positive if entropy is increasing, negative if entropy is decreasing, and staying the same would correspond to delta S equals 0. All right, so that's what I want to find out here. Then I remember that in this equation, T is temperature in Kelvin, and the lowest possible temperature in Kelvin is 0. So we're never going to have a negative temperature. So what that means is that the sign of delta S is going to depend solely on the sign of Q, the heat flow into or out of the system. So remember, Q is going to be positive in the case that the heat is flowing into the system of interest, and it's negative in the case that the heat is flowing out. Okay, so now if we want to determine whether the entropy of the metal increases, decreases, or stays the same, we need to determine if the heat flows into the metal, out of the metal, or if there's no heat flow into or out of the metal. Okay, so here we know that the metal is initially at 98 degrees Celsius, and then it's placed in this cool bucket of water, which is at 5 degrees Celsius. And so then the metal is initially hotter than the water. And we know that heat will tend to flow from the hotter object to the colder object. So that tells me that in this case, Q, the heat flow for the metal, is going to be negative. In other words, the heat is flowing out of the hot metal and into the colder water. All right, so now we're ready to think about delta S for the metal, which is just going to be Q for the metal divided by the temperature of the metal. Here, since Q for the metal is negative, that means that delta S is going to be negative as well. So in other words, the entropy of the metal is going to decrease. So I would pick answer 2 here. All right, now let's think about what happens to the entropy of the water. Okay, so to think about the entropy of the water, again, we want to think about, does heat flow into or out of the water? So here we'll talk about Q for the water. Then, because the water starts off colder than the metal and the metal is placed in contact with the water, we know that the heat is going to flow from the metal to the colder water. So that means that Q for the water is going to be positive. The heat flows into the water. All right, then we can think about the change in entropy of the water. It's going to be Q for the water divided by the temperature of the water. And then because Q for the water is positive, that means that the change in entropy of the water is going to be positive as well. And so then we can say that the entropy of the water is going to increase. All right, last question here. We want to know what happens to the entropy of the total system, which is the combined system of the metal and the water. Okay, so to answer this one, I want to think about delta S total, which is going to be delta S for the metal plus delta S for the water, which we can plug in our equations, is going to be Q for the metal divided by the temperature of the metal plus Q for the water divided by the temperature of the water. All right, and then Q for the metal and Q for the water are going to be related. Specifically, they have to be equal and opposite in this case. And that really comes from thinking about conservation of energy. And here we know that the amount of energy that leaves the metal as heat is going to have to be exactly equal to the amount of energy that enters the water as heat. So in other words, we could write Q metal here. It's really going to be minus Q for the water. Okay, and so I could go ahead and plug that in. Let's also plug in our temperatures, which remember have to be in Kelvin here. Okay, and so then the temperature of the metal, which is 98 degrees Celsius, is really going to be 371 Kelvin. And the temperature of the water, which is 5 degrees Celsius, is going to be 278 Kelvin. Okay, so let's go ahead and put it all together. We end up with minus Q water over 371 Kelvin plus Q water divided by 278 Kelvin. And so then this first term, the negative term, that term is dividing by a bigger number, so that's actually going to be the smaller term here. And so we're adding a smaller negative term to a bigger positive term. And so overall, we're going to get a result that is positive. So in other words, the overall entropy of the system is going to increase. So now with that last example in mind, let's go ahead and talk about the second law of thermodynamics. So one statement of the second law of thermodynamics is simply that when objects are in thermal contact with each other, so in other words, when heat can flow, the heat will always flow spontaneously from the hotter object to the colder object. So that's one way of stating the second law of thermodynamics, but it still doesn't really tell us why that tends to happen. And so why is it that the heat tends to flow from the hotter object to the colder object? Well, that's because total entropy of the universe tends to increase. So then mathematically we could say that delta S total has to be greater than or equal to 0, where delta S total is the total change in entropy of your system of interest. In other words, that's going to be like the sum of the individual changes in entropy of the objects in your system, which will be related to heat flow into or out of a particular object divided by that object's temperature. So really, we want to do exactly what we did in the last practice problem to think about delta S total. You'll want to think about, is heat flowing into or out of each object in your system? Find the change in entropy then of each object, add them up, and then that will tell you the total change in entropy of your system. Okay, and then in that last example, we did find that delta S total was positive. In other words, we did get an increase in the total system entropy. So this did obey the second law of thermodynamics. And that came directly from the fact that we did assume that the heat was flowing from the hotter object to the colder object when we made our assignments. All right, and then circling back to our discussion of reversible and irreversible processes from earlier in this lecture, the tendency of entropy to increase is really why certain processes are irreversible. So an irreversible process is one where entropy increases during that process. A reversible process is one where the change in entropy is equal to 0. Okay, and so this is something that's also referred to as the arrow of time or the asymmetry of time. And so this really comes from this idea that when you have this increase in entropy, it creates these irreversible processes. And so it's very clear which direction the process occurs in, right? So there's this distinction in the process going in the forward direction, which is physical, and the process going in the reverse, which would be non-physical. Okay, so now we're ready to talk about our very last topic for the semester, which is the application of the first and second laws of thermodynamics to heat engines. So actually, the development of heat engines was really why the study of thermal physics came about. So people wanted to know how to make an efficient engine. So that's really the basis for thermal physics, and we're going to learn how that happens today. So let's start by looking at this schematic of an engine that I have over on the right-hand side of the slide. And here I'll just mention that when I say engine, I don't mean the engine like the engine that's in your car. When we're talking about an engine here, what I'm really talking about is some working substance, usually a liquid or a gas, that can absorb heat, do work, and then give off waste heat. So when I say engine, be thinking gas usually, or sometimes liquid. All right, so what happens to this heat engine? So like I mentioned, the engine, which is usually the liquid or gas, is going to absorb some amount of heat. So we say that the amount of heat that the engine absorbs, we call it QH, and it's absorbed from the hot reservoir. All right, so QH is going to flow from the hot reservoir to the engine. A reservoir is just something that's large enough that it's at an approximately constant temperature. And here physically, when I talk about the hot reservoir, we're going to be talking about, for example, a place where coal is being burned. So it's just a hot location, right? So we're burning coal, that's the hot reservoir. And so then for example, water in your heat engine absorbs that heat from the burning coal. That absorbed heat is what we call QH, and then as the water in your engine absorbs that heat, it's converted into steam. Okay, so that's realistically what we're talking about in this first step of absorbing QH from the hot reservoir into the engine. Okay, and then the next step here is really going to be the goal of the heat engine. Here we're going to have this engine converting part of the heat that it absorbed from the hot reservoir into mechanical work. Okay, and so physically, what does this correspond to? Here we've already talked about the fact that we have water that absorbed some heat from the hot reservoir and got converted into steam. Now this step where we have our engine doing work is going to correspond to the steam usually expanding, doing something like turning a turbine or maybe pushing a piston, something like that. So in other words, it does mechanical work. All right, and then the last step here, we need to dump some waste heat. So waste heat QC is dumped into the cold reservoir. So this is just whatever heat didn't get converted into work, whatever remains has to get dumped out of the engine because this is a cyclic process, and so the engine itself has to get back to its original state. So it has to dump any extra heat that it wasn't able to convert into work. The place where it's dumped is what we call the cold reservoir. So physically, what does this correspond to? Here, this means that we have the steam cooling back into water, and so as it cools back into water, it's going to give off heat. Usually it's giving off heat into the environment or the surroundings. All right, and so then after that heat has been dumped, the waste heat has been dumped, then the system is returned to its original state, and so then the cycle can repeat. So the system will absorb more heat, it will do more work, and then it will dump more waste heat and just keep repeating. All right, so this is a cyclic process, and we can think about conservation of energy in this process. So remember, whenever you have a cyclic process, the change in internal energy due to that process is going to be equal to 0. And so here, when I'm talking about the change in internal energy of our system of interest, that's going to be the change in internal energy of our engine. So in other words, the working substance in the engine, that liquid or gas. Okay, so the change in internal energy of that working substance in our engine, we know is going to have to be equal to 0. And so what that means here is that all of the energy entering the engine is going to have to be equal to the energy that leaves the engine. Because here we have this cyclic process, so you can't have any leftover in the engine at the end of one full cycle. Okay, and so then when I think about the energy entering the engine, if you look at the arrows over here for QH, W, and QC, which are all defined to be positive values, you can see that energy that enters the engine is anything with an arrow pointing in towards the engine. So that's just going to be QH here. Energy leaving the engine is anything with an arrow pointing away from the engine. So that will be work done by the system here, the work done by the engine, and also QC will leave. Okay, and so then what we end up with here is QH, which remember is the heat entering the system or the engine from the hot reservoir, equal to W, the work done by the system, this is an output of the system, plus QC, which is the waste heat, heat that leaves the system, or in other words, leaves the engine and enters the cold reservoir. Okay, and then before we get to a more in-depth study of the first and second laws of thermodynamics with respect to our heat engine, I just wanted to show you the PV diagrams for a few classic heat engines. So first of all, we're going to start with the cycle that corresponds to the steam engine. This is referred to as the Rankine cycle, and I'll just go through each step of the cycle. It's plotted here on the PV diagram shown. Okay, so the first step is going from state 1 to state 2. Imagine the working substance here is water. It's liquid water to start with. And during this first step, you can see it's a straight vertical line, right? So that means that we're going to have a sharp increase in pressure at constant volume. In other words, here we say that the liquid is pumped to a high pressure at constant volume during that first step. Then during the second step, what happens is we have the water absorbing heat. For example, like I mentioned before, from burning coal, right? So you burn coal near the water, and so then the water absorbs heat from that burning coal. And then as it absorbs that heat, it transforms into steam. Here you can see that this is a horizontal line, so that corresponds to a process at constant pressure. Okay, and then next up we have the process that takes the system from state 3 to state 4, which you can see here is an adiabat. So really we're going to have adiabatic expansion of the steam during this process. So in state 3, we have a high pressure steam, and then it expands quickly, right? Adiabatically, it's going to expand quickly, and as it does that, it's going to turn a turbine or push a piston. In other words, this is where the majority of the work is going to be done by our working substance, which is our steam. All right, then the next step really is just this last step of getting back to the starting state. So to get back to the starting state, we need the steam to give off any extra energy that it wasn't able to use as work. So for this step, the steam is going to flow through a condenser. Here you can see that it's a horizontal line on our PV diagram, so that's going to correspond to a process at constant pressure. So it's going to flow through a condenser at constant pressure, and as it flows through that condenser, it's going to go back to its liquid state, and it'll be ready to restart this cycle. Alternatively, sometimes this steam is just released into the environment as exhaust, and more water is just added to the steam engine. Okay, so I hope you found that interesting. It's the inner workings of a steam engine, and like I mentioned, this is really the foundation of thermal physics. Okay, so I also just quickly wanted to mention the combustion engine here, which is like what most of you probably have in your car. And so the combustion engine in general operates on a cycle that's at least similar to the Otto cycle that I have shown here. So let's just go through the 4 different steps of the Otto cycle. Here you can see I have a PV diagram of the Otto cycle provided. All right, so the first step is going from state 1 to state 2. In this case, the working substance for the combustion engine is really going to be a mixture of gasoline, so vaporized gasoline, and then also air. So during this step, you have a vaporized air and gasoline mixture that gets injected into a cylinder in your car's engine, and then it's compressed adiabatically by a piston. Okay, then the next stage is what's called ignition. So here ignition is when you have a spark plug in that cylinder that ignites that gas and air mixture, and you can see here that that cylinder maintains a fixed volume, so that's why we end up getting this vertical line on our PV diagram. Okay, so that's the ignition phase, and you can see that at the end of the ignition phase you end up with a high temperature, high pressure gas. Okay, and then the next phase is what's referred to as the power stroke. So during this process, we have our initially high pressure, high temperature gas, and it expands rapidly. In expanding rapidly, it's going to push a piston, and therefore it's going to do work. That piston, when it's pushed, it will turn the wheels of your car, essentially. There are gears that make it turn the wheels of your car. Okay, so that's the power stroke, and then the last thing we need to do here is have the exhaust stroke. So during this phase, the gas it's done its job, it gets released into the atmosphere as exhaust, and then a new mixture of vaporized gasoline and air is drawn into the cylinder to restart the cycle. So this is what happens when you think about like a 4-stroke cycle in a combustion engine. And so again, I hope you just enjoyed a little bit of practical knowledge about how the combustion engine works in your car. Okay, and so now let's get back to our discussion of just general heat engines, and we're going to think specifically now about the laws of thermodynamics applied to these heat engines. So let's start with the first law of thermodynamics, which tells us that delta U for a system, the change in internal energy of a system, is equal to the total amount of heat that enters or leaves that system minus the work done by the system. And then here, our system, remember, is just going to be our engine, or rather the working substance in our engine, so usually a liquid or a gas. And so then we can think about these different terms in our first law of thermodynamics. Delta U, the change in internal energy, remember, is going to be equal to 0 because that working substance is going through a cyclic process. So it starts in some state, it goes through some cyclic process, and it ends up back in the same state that it started in. And so then when we think about delta U, which is U final minus U initial, The final internal energy and the initial have to be the same because it's in the same state, and so delta U has to be equal to 0. Okay, now we can think a little bit more about Q total, which is going to be the total amount of heat flowing into and out of this engine. So here we know that QH is flowing into the engine, QC is flowing out of the engine. So the total amount of heat that's going to be entering or leaving the engine is going to be QH minus QC, where we've defined QC to be a positive value, right? So I'm subtracting QC because it's leaving the engine, and QC itself is defined to be a positive value. Okay, and so then what we end up with is 0 is equal to QH minus QC minus W. All right, so I can rearrange that equation, and when I do, I get QH is equal to W plus QC, which makes sense because then I have QH, which is the total amount of energy entering my engine, equal to W plus QC, which is the total amount of energy leaving my engine. All right, so the next thing we want to think about is something called efficiency. So when I think about the efficiency of the engine, what I'm really going to be interested in is how much benefit do I get out of this engine for a particular amount of cost. So here, when I think about the cost of running the engine, it's really going to be the total amount of energy that you have to put in to the engine to start with. And so that's going to be QH here. That's going to be the cost of running the engine. All right, then when I think about the benefit of the engine, well, that's really going to be the work done by the engine. So the benefit here is going to be W. And then what is QC? That's really the waste. All right, and then the efficiency, remember I mentioned, is going to be the benefit per cost. And so here we've identified the benefit is going to be the work done. The cost is going to be QH, which is the heat absorbed by the engine. And so we end up with efficiency equal to the work done by the engine divided by the heat absorbed by the engine. Okay, we can rewrite this a little bit. If we rearrange this top equation that QH is equal to W plus QC, you can rearrange and find that W, the work done by the system, is going to be equal to QH minus QC. And so I've just plugged that in here. So I've plugged in W is equal to QH minus QC. And the reason why I did that is you just get this nice relationship. You can divide each term by QH, and you end up with the efficiency is equal to 1 minus QC divided by QH. Okay, and so you can see that your efficiency is going to be greatest. It'll be greatest with a value of 1, ideally. It would be greatest with a value of 1 in the case that QC is equal to 0. So in other words, you have no waste. So it's kind of a nice way to think about the efficiency here. All right, but it turns out that it's actually not possible to get 0 waste heat. So in other words, QC is never going to be equal to 0. And the reason why is really the second law of thermodynamics, which tells us that the entropy of the universe tends to increase. Okay, so this second law of thermodynamics, it's really going to limit our possible efficiencies here. And so we want to know what is the limit on the efficiency due to the fact that the entropy of the universe has to increase. Okay, so to analyze that, we're really going to think about what is the total change in entropy due to one cycle of our engine operating. So when we think about the total change in entropy in this case, we're really going to be thinking about the total change in entropy of the engine plus the change in entropy of the hot reservoir plus the change in entropy of the cold reservoir. Okay, and so then the total change in entropy for one cycle of our engine is going to be the change in entropy of the engine itself plus the change in entropy of the hot reservoir, which I'm calling delta SH, plus the change in entropy of the cold reservoir, which I'm calling delta SC. Okay, so now let's just go ahead and think about each of these individual terms, and I'll remind you that in general for a quasi-static process, which we're going to be assuming is the case here, the change in entropy of a particular object is going to be equal to Q, the heat flow into or out of that object, divided by T, the temperature of the object. Okay, so let's go ahead and get started with delta S engine, so in other words, the change in entropy of the engine. Okay, so to think about this, I'll remind you that S is a state variable, which means that it only depends on the state that the engine is in and not how it got there. So then when we think about the cyclic process that the engine undergoes, it's going to start in some initial state and then it's going to end up in the same final state that it started in. Okay, and so then since the entropy only depends on the state, it will be the same in the initial and final states. They're the same states, so the entropy will be the same. And so delta S for our engine in one complete cycle is just going to be equal to 0. All right, next let's think about the change in entropy of the hot reservoir. Okay, so for this, we're going to be thinking about our equation that delta S is equal to Q divided by T. Here I'll define the temperature of the hot reservoir to be TH, and then we just need to think about what is the heat entering or leaving the hot reservoir. So going back to our little diagram on the top right-hand side corner of this slide, we can see that QH is the amount of heat that leaves the hot reservoir. And remember, QH is defined to be a positive value. So for heat leaving the hot reservoir, that means that I'm going to be interested in minus QH. Okay, and so then delta S for our hot reservoir is equal to minus QH divided by TH. All right, lastly, we want to think about the change in entropy of the cold reservoir. So for the change in entropy of the cold reservoir, I'll define the temperature of the cold reservoir to be Tc. And then we need to think about what is the heat that enters or leaves the cold reservoir. So again, looking at our diagram up here, we can see that an amount of heat Qc is entering the cold reservoir. Once again, Qc is defined to be positive, and so then because the heat is entering the cold reservoir, the change in entropy will also be positive, and so we end up with delta S for the cold reservoir equal to plus Qc divided by Tc. Okay, so now we're ready to calculate the total change in entropy of the universe due to one cycle of this engine. So all I've done here is I've just plugged in that delta S for the engine is 0, delta S for the hot reservoir is minus QH over TH, and delta S for the cold reservoir is QC divided by TC. And then we know that this total change in entropy has to be greater than or equal to 0 due to our second law of thermodynamics. And so what I end up getting here is that QC divided by TC has to be greater than or equal to QH divided by TH. So I've just rearranged this top equation here. And I'm going to rearrange one more time. Here, QC, QH, TC, and TH, they're all defined to be positive values. So I can go ahead and think about dividing both sides of this equation by QH and multiplying both sides of this equation by TC without having to worry about changing the sign of my inequality here. And so what we end up with finally is QC over QH has to be greater than or equal to TC divided by TH. And this all just comes from the condition that the total entropy of the universe has to increase. In other words, it comes from our second law of thermodynamics. Okay, and so then I have something that looks like QC over QH, and so I can relate this to my efficiency. So specifically here, when I plug this condition in, I find that the maximum possible value of my efficiency is going to be 1 minus TC over TH, and that comes from the fact that QC over QH is always going to be bigger than TC over TH, and in general, the efficiency is going to be less than or equal to 1 minus TC over TH, where remember TC is the temperature of the cold reservoir and TH is the temperature of the hot reservoir. Okay, so let's talk about this resulting equation for a moment here. So it turns out that how close your efficiency is to this maximum value of 1 minus T cold over T hot will depend on the type of process that your engine uses. And so to get E exactly equal to 1 minus T cold over T hot, you need a process that creates delta S total of 0. So that's going to give you then the maximum possible efficiency, and we'll talk about how to achieve that in a moment here. But in general, for a fixed type of process, then you can see that you can also increase the efficiency by either decreasing the temperature of the cold reservoir or by increasing the temperature of the hot reservoir. Okay, and so then you would ideally want T cold, the temperature of your cold reservoir, to be as close as possible to absolute 0, which is of course practically hard to achieve, and you want your hot reservoir to be as hot as possible to get the maximum possible efficiency. All right, let's go ahead and do a little bit of practice in dealing with heat engines here. So we have a heat engine that does 1,750 joules of work and discards 7,950 joules of heat to the surroundings. And we want to know here how much heat does the engine need to absorb from the burning of coal, or in other words, from the hot reservoir. Okay, so to answer this, I would think about making a list of known information here. So let's start with our knowns. So first of all, I see here that the engine does 1,750 joules of work. Okay, and then we're told that the engine discards this amount of 7,950 joules of heat. And so what that's really going to be is the waste heat QC. Okay, so my waste heat QC is going to be 7,950 joules. All right, next we want to know our thing that we're looking for here, which is how much heat does the engine absorb from the burning of coal, or in other words, from the hot reservoir. So that's going to be Q hot. That's the thing we're looking for here. And so to answer this question, I'd be thinking about conservation of energy. So remember, the total energy that enters the engine has to be the total amount of energy that leaves the engine. So here, the total amount of energy that enters the engine is just Q hot. And then the total amount of energy that leaves is the work done by the engine plus the waste heat. Okay, and so then Q hot is just going to be equal to the sum of 1,750 joules plus 7,950 joules. And so when I added those together, I got 9,700 joules, or in other words, answer C here. Okay, so now thinking about the same engine, we want to know what is this engine's efficiency. Okay, so to answer this one, I would remember that the efficiency E is equal to the benefit of the engine divided by its cost. Okay, and so the benefit of the engine is really the work that it does, and then the cost is the amount of heat that you have to put in. So that's going to be W divided by QH. Okay, then we know the amount of work done by the engine is 1,750 joules, and from the last problem, we know that QH is 9,700 joules. Okay, and so when I calculated that out, I ended up getting an efficiency of 0.18, which is the same thing as 18%. So I would go ahead and pick answer B here. Okay, so now let's talk a little bit more about this efficiency equation. E is less than or equal to 1 minus T cold over T hot. Okay, and so then you can see that the maximum possible efficiency is going to be equal to 1 minus T cold over T hot. And I mentioned before that how close the efficiency is to this maximum possible value is going to depend on the type of process that the engine uses. And so our goal now is going to be determining what type of process is required to get the efficiency of the engine exactly equal to this maximum possible value. So to do that, we're going to think back to how we derived this efficiency equation with this inequality in it. And remember that inequality really came from the second law of thermodynamics, which tells us that the total change in entropy of the combined system of the engine, the hot reservoir, and the cold reservoir has to be greater than or equal to 0. So then if I want to achieve the equality in my efficiency equation, I need to achieve the equality in my delta S total equals 0 equation. So in other words, if I want maximum efficiency of 1 minus T cold over T hot, I need a process for which delta S total, the combined change in entropy of the engine, the hot reservoir, and the cold reservoir, is exactly equal to 0. Okay, and so it turns out that there's a well-known process for which this is the case. It's called the Carnot Cycle, and the Carnot Cycle has 4 parts. So we'll just briefly go through each of those 4 parts, and I have a PV diagram corresponding to those 4 parts plotted down below. Okay, so this first step, step A, is an isothermal expansion of the working substance in the engine. Isothermal, remember, means at constant temperature, and specifically here, the temperature of the working substance in the engine during this step needs to be approximately equal to the temperature of the hot reservoir. So in other words, this step needs to occur at temperature TH. All right, then during this step, the working substance is absorbing energy QH from the hot reservoir. The next step, step B, is an adiabatic expansion of the working substance. So during this step, the substance is going to be expanding, it's going to be doing work. Adiabatic, remember, means that there's going to be no heat exchange with the surroundings during this particular step. And also during this step then, because there's no heat exchange, we know that there's going to be no creation of new entropy. And then something else important that happens during this step is that as the gas or working substance of the engine expands, it's going to cool off. So remember, it started off at temperature TH, which was the temperature of the hot reservoir, and by the end of step B, it needs to be at temperature TC, which is the temperature of the cold reservoir. Okay, so then it needs to be at that temperature TC to start off step C, which is an isothermal compression of that working substance. Isothermal, remember, means at constant temperature, and specifically here, as I mentioned, the temperature needs to be approximately equal to the temperature of the cold reservoir, TC. Okay, so then during this step, what's happening is that this engine is giving off that waste heat to the cold reservoir. All right, the last step, step D, is an adiabatic compression of the working substance, and the main point of this step is just to warm the substance back up to its temperature TH so that we can restart the cycle and start absorbing heat, doing work, and carrying on. Okay, and so then it turns out that this complete cycle creates no new change in the total entropy of the combined system of the engine, the cold reservoir, and the hot reservoir, and so that makes it maximally efficient. So in other words, it's going to achieve this Emax of 1 minus T cold over T hot. But I will mention that while it's maximally efficient in terms of energy here, so it gives you the maximum amount of work for the minimum amount of cost, in other words, the minimum amount of heat input, it turns out that it's actually very, very slow. So these isothermal expansions and compressions, they have to be super slow so that you're not changing the temperature of the working substance. And so that means that this is not going to be used very often. You might be wondering like why this isn't used in your car or anything like that. And that is why. So it's because it's exceptionally slow, and so it's not really very practical to use the Carnot cycle. Okay, so let's do a little bit of practice here. So we have a power plant that has steam at 540 degrees Celsius that is cooled to water at 20 degrees Celsius. And we want to know if the plant operates with a Carnot cycle, what is its efficiency? Okay, so to answer this question, remember that for the Carnot cycle, the efficiency is equal to the maximum efficiency of 1 minus T cold over T hot. Then looking at our problem statement, we see that T cold is the temperature of the water at 20 degrees Celsius, and T hot is the temperature of the steam at 540 degrees Celsius. To use this equation, though, we're going to have to convert into Kelvin. So when I did that, I got T cold of 293 Kelvin and T hot of 813 Kelvin. Okay, then I went ahead and I calculated T cold over T hot. When I did that, I ended up getting 0.36. And so then Emax is going to be 1 minus 0.36, which is going to be 0.64, or in other words, 64%. Okay, and so I ended up getting answer B here. All right, so now we've talked about heat engines. Let's go ahead and talk a little bit about refrigerators, which are actually just heat engines that operate in reverse. So whatever cyclic process you use to get a heat engine, if you run it in reverse, you'll get a refrigerator. All right, so let's talk about it a little bit. I have a schematic over here on the right-hand side where we have a refrigerator which is going to contain some working substance, so like a liquid or a gas, just like we talked about for our engine. And then you can see that you put some work into your refrigerator. So I'm putting in an amount of work W. That's going to be work done on the system of the refrigerator. And that work is going to be done to be able to remove some amount of heat, Q cold, from the cold reservoir. And that cold reservoir is the thing that you want to cool down. So that's going to be like the inside of your refrigerator in your kitchen. So the cold reservoir in this case is the thing that you want to cool down. And so practically then this is achieved by running some cold fluid, so that's going to be the working fluid of your refrigerator, around the outside of the cold reservoir, and then that cold fluid is going to absorb heat from inside the cold reservoir. All right, next, after that cold fluid has absorbed heat from the cold reservoir, it needs to dump some waste heat, and so it will dump that waste heat into the hot reservoir. Usually you can feel like underneath your refrigerator, you can feel some warm air blowing out, so that's going to be your refrigerator dumping waste heat. And then once that cooling liquid, that working substance of the refrigerator, has dumped its waste heat, it's going to be returned to its original state, and so then it's ready to have more work done on it so it can continue circulating around and pulling that heat out of the cold reservoir. All right, let's think a little bit more in detail then about the different energy exchanges during this process. So first of all, I'll remind you that this is a cyclic process, just like in the heat engine. And so then the change in internal energy of the working fluid in the refrigerator is going to be equal to 0. So in other words here, what that means is that the total energy entering the refrigerator has to be equal to the total energy that leaves the refrigerator. And when I say the refrigerator, I mean the working substance. Okay, and so then when I look at this diagram, you can see that the energy that enters the refrigerator is going to be Q cold and the work done on the system. The energy that leaves is going to be that waste heat. So what we end up with here is going to be W plus Q cold is equal to Q hot. Okay, we can also think about the energy in terms of the first law of thermodynamics here. We're going to have to be a little bit careful about the signs, but in general, remember delta U is equal to Q minus W. Here, delta U is going to be the change in internal energy of the working substance of the refrigerator, which we know is equal to 0. Q total, remember, is going to be equal to energy that enters the refrigerator, Q cold, minus energy that leaves the refrigerator as heat, Q hot. And so then I end up with Q total in this case is going to be Q cold minus Q hot. And then this is the part where it gets a little tricky on the signs. Remember, W in our first law of thermodynamics is defined to be the work done by the system. So here, the work done on the system is W. And so what that means is when we think about the first law of thermodynamics, we're really going to be subtracting off minus W minus the work done on the system to get the work done by the system. Okay, and so then we can rearrange this equation, and what we find is that W is equal to QH minus QC, which agrees with what we found on the last slide. All right, now we want to think about the efficiency of the refrigerator. Really, we're going to be thinking again about what is the benefit and what is the cost of the refrigerator. So here the benefit is the amount of heat that we remove from the cold reservoir. So QC is going to be our benefit. The cost is the amount of work that's required to do this, and so then the cost is going to be W. All right, and then the waste is just going to be QH. So then we can define something that's similar to the efficiency, but it's called the coefficient of performance for a refrigerator. It's still just going to be benefit over cost, but for a refrigerator, the benefits and costs are different than for a heat engine. So here we're going to have benefit of QC divided by the cost, W. You can plug in the fact that W is equal to QH minus QC into the denominator here and do a little bit of algebra to find that the coefficient of performance is equal to 1 over QH divided by QC minus 1. Okay, then we can think about the limits on this coefficient of performance in terms of the second law of thermodynamics, just like we did when we were talking about engines. So once again, we can think about the change in the total entropy of the system, which we know has to be greater than or equal to 0. Okay, and so then that total change in entropy of the combined system of the refrigerator, the cold reservoir, and the hot reservoir is going to be the sum of the change in entropy of the refrigerator, which we know is going to be 0 because it's a cyclic process, plus the total change in entropy of the hot reservoir. Here, the amount of heat that enters the hot reservoir is QH, and the hot reservoir is at temperature TH, and so the change in entropy of the hot reservoir is going to be plus QH over TH. And then we have the change in entropy of the cold reservoir. Here we have heat QC leaving the cold reservoir, and the cold reservoir is at temperature TC, and so we end up with delta S for the cold reservoir of minus QC over TC. Okay, and so then we can add those changes in entropy together to get the total change in entropy of this combined system. And then what we end up with after a little bit of algebra, setting that total change in entropy greater than or equal to 0, what we find is that QH over TH is going to be greater than or equal to QC over TC. We can rearrange that to get it in terms of QH over QC to plug into our coefficient of performance equation. And then what we end up with is that the coefficient of performance is always going to be less than or equal to TC over TH minus TC. Okay, so it turns out that this coefficient of performance actually can be greater than 1. So unlike the efficiency of an engine, which is always going to be less than 1, so we can get a pretty high efficiency or coefficient of performance for the refrigerator. But it turns out that the coefficient of performance is still limited by the second law of thermodynamics and the fact that the total change in entropy has to be greater than or equal to 0. Okay, let's do a little bit of practice here. We have a refrigerator that operates at 23% efficiency, and it requires a work input of 1,800 joules. We want to know how much heat does it remove from the cold reservoir, or in other words, from inside of the refrigerator. First of all, we know that the coefficient of performance for this refrigerator is 23%, or in other words, 0.23. Then we know that the work done on the refrigerator is 1,800 joules. And we know that the thing we're looking for is the amount of heat that this refrigerator removes from the cold reservoir. So that's going to be QC. Okay, and so that's what we're looking for. We can find it because remember the coefficient of performance is equal to the benefit, which is QC, divided by the cost, which is W. Okay, and so we can rearrange that equation and we get QC is going to be equal to W times the coefficient of performance. So in other words, it's going to be 1,800 joules times 0.23. So when I multiplied that out, I ended up getting answer A here of 414 joules. Okay, so that really wraps up our study of the second law of thermodynamics. For completeness here, I will just briefly mention that the third law of thermodynamics tells us about absolute zero. So specifically, it tells us that entropy approaches a constant value at absolute zero. All right, so that's it for our chapter on the laws of thermodynamics, and that's it for this semester. We have lots of practice coming up in class on engines and refrigerators, so I will see you guys then.